How are you?
Yeah. 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 Little retrospective for Prince. Keep me in a good mood out here, right? Hopefully everybody else is going like, okay. So, hey, how are you? Haven't seen you in a while. You're back on campus. Are you still on campus? You are still on campus. You are? Oh, good.
I know. My lucky.
Oh, good. No. Yeah. Oh, wow. Got the music. We'll see. Hopefully entertaining. We'll see. Yeah. Yeah. That's definitely been moving that direction for a while. Yeah. 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 So, well, good. I had a wonderful sabbatical last year. Part of the time at University of Dresden.
Still coming or the next time you know that they're doing. It's my honor to introduce our last speaker of the semester, my good colleague Alison Flatau. Alison really has known for introduction. You all know her very well, but Alison is a, I think remember we got a call. She actually, I don't know, had your bachelor's in engineering.
I did.
And then master's and PhD in mechanical engineering. And she was actually a program director at SDOF for 4 years prior to coming to Maryland in 2002, which I very much trying to remember. Alison is a fellow of a lot of my students today. She's going to give us a snapshot about some of the great work that she's doing in her group. So we know what we're doing.
Thank you. So welcome everybody. This is going to be about electromechanical system modeling, which is partly a plug for grad course I teach that's very systems oriented and should attract students from a lot of disciplines, and everything from civil, mechanical, electrical, aero, and it sort of is built into the title. Electromechanical is a little misleading because it covers a lot of different domains. And right at the end, I'm going to tie it together with my research group with one or two projects that are going on. So, thank you for the invitation. I do have an outline, and I think it's doing that same thing again. There we go. So I'm going to start with a demo to have an appreciation for why I'm going to devote the rest of the time to talking about this. I'll give my pitch for how the modeling works, my pitch for 788E. I'll talk a little bit about magnetostrictive materials and how they work, because that's been the basis of a lot of the research and publications I've been involved with, opportunities to work with wonderful students. And finish up with a little bit about using electromechanical system modeling to do some simulations and predictions for impedance matching the electrical side of a magnetostrictive energy harvester. So the demos, before I get to the demos, just in general, when I talk about an electromechanical system, it's mechanical, it's fluid, it's mechanical, it's thermal. There are probably any places you can put power. You can probably come up with a model to couple the power in one domain, be it acoustic, magnetostrictive, thermal, to the rest of the domains that you might want to. The easiest example that everybody's got an intuitive sense about already is a loudspeaker, permanent magnet. Everybody's probably seen a loudspeaker, maybe not torn it apart like in these pictures here, but if you take off this front piece, then you get different parts back here, and ultimately there's a little copper coil that's wrapped on paper that's sort of, they call it a spring. It's a spider. You can see the spider here that suspends this coil over the top of a permanent magnet, or at least a flux piece, pole piece of a flux circuit that has flux leakage as copper has an AC current going through it. It moves relative to that fixed permanent magnet and moves the paper cone. So that's one demo. I'll be getting back to that as the talk goes on. Here's a cutout. That's the gray part is a permanent magnet. This white part would be the flux path, and where there's an air gap between the center pole piece and the side pieces, it's magnetic flux. This red is the copper coil that's stuck on the paper cone that has ripples in it, the spider, and then the cone that you see when you look at the speaker. And those have some compliance N. The whole thing has some mass M. You put in to your system a current and a voltage, and you get out sound pressure, and particle velocity. So the rest of the talk is going to be about how you get from one to the other. And then the demos, this is also an energy harvesting that's magnetostrictive. This little tiny piece right in there, wrapped by a little copper coil, is being shook and turning on that light. So that's one example of an energy harvester. This is a colleague in Kanazawa University in Japan that does this type of work, and he also does little motors. That same size device sitting in there can do at least 2D motion. Okay, so I think this is where I get to use the blank feature and point out live demos are always much more fun. So the sound was part of the demo. So this is a piece of magnetostrictive material, and I think I'm overloading it. I turned it up too high. So that's a piece of magnetostrictive material. If I pick it up, it's just pushing against air. Air is really compliant and gets out of the way. So it's very hard for this thing to put energy into the air. On the other hand, if I put it on the table, the table's kind of stiff. So this thing can punch the table. And the table, in turn, makes a really good loudspeaker. So that's demo one. Oh, hey, John, you guys just missed my first part demo. So the demo, this is just one of two demos. I've got a chunk of magnetostrictive material in here, pushing against air. Air is compliant, gets out of the way. If I put it on the table, on the other hand, oh, I'm going to keep it on. So that's one demo, and then the other demo. Okay, so I can turn that off until the end of the show. The other demo is right here, and this is one of those classic loudspeakers. It's a permanent magnet-based loudspeaker, and I don't know how many of you have taken your loudspeakers apart. Yeah, see, I'm not the only one who does that. So I'm going for, this is about 200 hertz. Everybody can hear that, right? It's because it's in the loudspeaker. Just want to get out the box. Hopefully you guys notice the difference. And if I put it back in the box makes a difference. And sort of the finale of the talk is going to be me modeling this, or at least measuring it and showing you the difference. I will point out that it makes a difference at low frequencies. If I crank this up to maybe 1,000 hertz or so. Everybody still hear that? That's 800. Speaker's not making the speaker enclosure. Makes a little difference still, but clearly not as much as, okay. So let's hear it for demos that work. I love a demo that works. Okay, so I'll unblank this, and that's why you would want to understand how to do electromechanical system modeling. It will allow you to design the shape of that speaker box to get sound out at the frequencies that you want sound out. So the approach, and again, this is a synopsis of what goes into IAI 788E, and it's based on basic electronic modeling, electrical circuit modeling, network modeling. There's a lot of different names. And so with apologies, those of you with the background in EE, this next 5-10 slides are going to be very, very basic, but for those of you with aero or civil or other backgrounds, it's setting the stage for how this whole concept is going to work. Vocabulary, these are words that apply not just to EE, they apply to every physical domain, be it hydraulic, chemical, thermal. In whatever that physical domain is, you can identify components that are either active or passive, coordinates that are going to be our flow through and throw across quantities, node loops, transformers, and gyrators. And I don't have a specific slide on impedance and admittance, so with apologies, I may randomly toss those words in because they're very convenient, but I'm going to at least take enough time to define those and show you why they work really well for modeling this loudspeaker and that table speaker. Okay, so basics, really fundamental definitions. You'll see as I go forward, this color scheme is going to show up again and again. The basic coordinates, the active components or sources typically are associated with 2 coordinates. The product of the coordinates is power. Volts times amps gives you watts. For the purposes of modeling, we always go to extremes. So either you have a constant current source and the voltage adjusts, or you have a constant voltage source like your wall, and the current adjusts as needed to get whatever the power you're rated at. EEs have 3 passive components, 2 of which store energy, and 1 of which dissipates energy. Capacitors, inductors, and resistors. I go through those one at a time. I've got a pretty basic circuit here, RLC, with in this case, I used a current source. Little symbols here, that would be in this box for a current source or a straight bar for a voltage source. The little subscript not indicates which one's current, which one's constant. The next one, resistors with units of ohm dissipate power as, or energy as heat. This is sort of the sum total of equations. I've got one for each component. So this one's directly proportional. Current, the 2 coordinates are scaled by the component. Inductors in units of Henry store magnetic energy in the form of magnetic flux. Relationship, the inductance L is proportional to the time of change of current. Very convenient for the modeling I'll be doing. I'm going to use linear time invariant systems. Means it doesn't matter if it's Thursday or Wednesday. If I do X, I'll always get Y. So linear time invariant systems, I just model current E to the j omega t, and then I can say the relationship between voltage and current is by j omega L. And the capacitor, this one stores electrostatic energy in the form of electric field or charge, and that's actually the time rate of change of voltage is proportional to the current in this case. And so j omega c, the denominator with I. So kept the format the same. Pretty basic. So that's my active components, passive components, coordinates. I've got nodes, those little dots, sort of the terminals at the end of each component would be a node. This shows the standard symbols for these component sketches. We have a flow through and the difference across quantity. And this is a fascinating concept because people have been doing electromechanical system modeling for over a century, and as you go to different domains, everybody uses what they want. And there's reasons sometimes you want one as a flow through and the other as a flow across. There's advantages. So by convention, you'll see I use that phrase a lot. By convention, current is the flow through, and you measure the voltage drop across a component. And let's see, the next one, this is more on the nodes. Basically, down here where everything's short-circuited, that's basically one node. In between those two components is a node. In between these three components is a node. Over there's a node. Kirchhoff's node law says the sum of all current going into or out of a node has to sum to 0. And Kirchhoff's loop law says the sum of the voltage drops around any loop in a circuit is going to be 0 also. And it doesn't matter if you go clockwise or counterclockwise, it always is going to measure the drop from 1 to 4, 4 to 3, 3 to 2, 2 to 1, it's going to add to 0. That's our basics. Now remember this chart, I put this up when I started, introducing electrical components. The same is true for translational components. You can write out the, and this, you want to find coordinates that have power as a product. So keeping track of units, force and velocity meet that criteria. As far as which ones to flow through and which ones to flow, that's why I say I'm going to use force as the flow through. And there are other text references that do other things, but units, SI units. I work in compliance. A lot of mechanical types will use stiffness. 1 over stiffness is compliance. But storing kinetic energy, potential energy, and dissipating power. Recognize a theme here, right? This is darn similar. And rotational components, moment and angular velocity. Product is power. I got a couple of different symbols. Rotational inertia stores kinetic. Rotational compliance stores potential. Rotational damping or friction dissipates. And acoustic goes through a little bit, and you get pressure and volume flow rate. You have mass stores kinetic, compliance stores potential, damping dissipates power energy. And then, remember this equation sheet? I said those are going to be my equations. Don't pay attention, you'll think it's the same slide, but there's the next slide with force and velocity, there's the next slide with angular velocity and moment, and pressure and volume. It's all the same. Everything carries through. So once you start, the way I model it, with force being the through quantity, usually we model mass as a capacitor. Okay.
Actually, you have to mass the bit of the inverter, you have to have it grounded.
I do always ground by masses.
Yeah.
I do always
The
ground.
inverter actually was a big investment. It was actually for racing cars. Because the spring being the inductor,
No, I didn't. Yeah? Oh, I don't know about that. I'll have to read up. See, this is why I come to these talks. I look. Okay, well, I'd agree with that. You have to pay attention to everything. Is captured by, I'm sorry. Oh, okay. Yeah. Mm-hmm. Mm-hmm. Okay. I'm ready to learn more. So the art of applying this comes in understanding how to identify that nodes have the same deflection. So for instance, this mass deflects with respect to ground. That's what you were just pointing out. Okay, well, please come to my course. Yeah. Okay. Not analyst. Well, so this is the schema. The idea. Yeah. Well, the mass moves relative to ground with a certain velocity that is also the same velocity as the top of the spring and the damper. And so for that reason, they are shown, all three of them are acting in parallel. Makes for a very simple circuit. And I have a model. I picked some numbers. And then I used LT Spice. Depending on the time, maybe I'll show it at the end. But if you run this model, LT Spice is free. You download it in your system. Oh, absolutely. Absolutely, yes. So I stick with SI units. So this is my little model here. I have velocity in green, and then you just take the velocity, divide by 2 pi times the frequency, or multiply to get displacement and acceleration. And this is for my, that's just for the excitation you see there. And I think I'll show afterwards how fast this is to calculate. The thing that's really nice about LT Spice and the other simulators like this is you do get output in meters per second when you use a voltage probe, or newtons for the force when you use a current probe. You can plot displacement just by scaling velocity and acceleration. You can use the step and or parameter commands to do parameter sweeps. Mine that I find particularly convenient is I stick a little series resistor between the ground and the real ground, so that I can measure the force going into the ground through both the spring and the damper. I'll show you that in the next one. And then you can do time domain, frequency domain. You can get pretty fancy. So here's that same parallel spring mass damper, mass damper and spring actually. And then I put this to measure the force to ground. I've either got AC or transient for time domain. I can either do a single variable or a list. And so the next plot I show the resonance. I picked for a mass of 1 kilogram. I had a resonance at 2,500 hertz. And so if I take the mass up to 4 and 9, the resonance should drop by a factor of 2 and 3. And then I've got a couple of different dampings in there. If you plot those in the frequency domain, you do see the dropping here. This is in dB, and you see the phase. I've got very little damping, so it goes right through 90 degrees at resonance. And if I switch it to the linear domain, this is the force to the ground. And 220 Newton. It's just a function of the parameters that I selected, but still being able to come in this fast and calculate things like that, interrogate, inspect. It's actually very convenient. You can see there's the initial case, the 1 kilogram case for the 3 different damping cases, 4 kilogram and 9 kilogram mass. So it's linear, you get your units out. And then the last thing that's very convenient about using LT-SPICE, and the thing that really marries together all the different domains, is transformers and gyrators. And EEs, again, I'm very familiar with this. The example here is a step-down electrical transformer and a step-up one. If you have a voltage source here, you want to measure something over there, and you have turns ratios, you have a lot of turns on this side and a few turns on that side, you get a lower voltage and a higher current, but the same power. Power transforms across transformers with no changes in magnitude. Power stays constant. And if you've got losses, throw in a resistor to say I've got losses. If you've got energy stored, throw in an inductor or capacitor. They'll store the energy. But the transformer itself, as we're modeling it for our LTI systems, the linear time invariant systems, we're saying across that transformer, everything on this side turns into power on that side. Which means that, here's the symbols here. I've got the, so reiterating this in bold red, because this is the takeaway point from the last 2 slides. Power on the left is equal to power on the right. This would be the network symbol, would just be a box. K in this case would be the turns ratio. And you can either have it positive or negative depending on if your voltage is going. I'm sorry? I'm sorry? So you will, so throw in a resistor half on this side and half on that side, and say that the transformation in spite of the parasitic resistor is 100%, and build in something to model that. Because what that lets you do is then say, well, I've already identified my coordinates in the mechanical system for power. So it's going to let me transform to the mechanical domain, and I can transform from the mechanical domain to the acoustic domain. So this is my loudspeaker case. You can go back and forth. If it's a microphone, you're probably going the other direction. It works best for linear models. Mm-hmm. Okay. Okay. That's why it's such a good tool for modeling across the yeah. Yeah. No, I appreciate it. Yes. Mm-hmm. And for TVs, so if you can go to say Magnetostrictive Yep. We do, so this is based on what my colleagues at Dresden are doing, and they do distributed systems, and they do some nonlinear systems. They're doing hydrogels right now. That's their latest push for fluidics. Transformers, one of the things that's elegant about transformers is you can pull everything to one side or the other. So if you have current and velocity on that side, force, current and voltage, force and velocity, you can model using the transformer coefficient Y, you can get the capacitance from the electrical side into a mechanical equivalent component, so that will show up as a force and velocity scaled properly. And same thing, the compliance from the mechanical side will come across. You just have to follow the form to see whether it's a capacitor or inductor network symbol. What that lets you do, this would be the loudspeaker model where electrical source on the end and the acoustic output that you all were hearing on the far right, recognizing that the interaction, so the magnetic flux in the gap and the length of the coil turns into the transformer coefficient. You'll see there's always going to be this relationship of A and 1 over A, or whatever your Y and 1 over Y for the transformer coefficients, because at least in the work I'm doing, we're treating things as literally bidirectional across a transformer, just power going from one side to the other. And so with this, we've got pulling everything into the mechanical side. So we have the acoustic here comes over the mechanical side, scaled by the area, cross-sectional area, the moving baffle. The electrical side comes over onto the mechanical side in this model. And you can start looking at frequency response functions in a single domain. This is a little bit of what you already heard. This is with a bass reflex speaker, where it's got the port here, which the speaker does. The whole bottom. It gives a real boost to that low frequency. Usually people start hearing around 20 hertz up to 20 kilohertz in a good young ear. And I think most of you sounded like you could hear the difference when I was down at 100 hertz, maybe not so much at 1,000. So the next topic, and I'll go back to more demos, would be magnetostrictive material. So this has been the focus of my research for a number of years. If you have a rod of magnetostrictive material that starts at length 0, arbitrarily set here, and then you'll apply a DC magnetic field with a permanent magnet, for instance, you change length to, arguably, you would want to select your DC bias to make it half as long as it's going to get, and then you would put a coil around the permanent magnet and cycle an AC signal to operate about your biasing point, your mid-length. That's called the burst region of the magnetostrictive behavior. That's called the direct effect. That's how you make an actuator out of magnetostrictive, the little moving platform. That's was using 3 little rods behaving in this manner with the controlled signals. Internally, there's arguably magnetic domains. If you compress a rod, it'll start perpendicular, and at the atomic level, you get strain from rotation of magnetic domain. There's much fancier explanations, but that's the basics. Also, transformer coefficient or transduction coefficient, D3, you apply a magnetic field in the 3 direction rod length, and you get strain in the rod length. Basically, just draw a straight line through that, those 3 dots, and that's your operating region. And that would be your relationship between strain and applied magnetic field. Applied magnetic field is proportional to the current through the coil. So it gets back to your electrical side. That's down here, H is equal to Ni. Sensing is the inverse of this, where you apply a biasing field, and then, so that's a permanent magnet, is already got all the domains aligned along the length, and then as you apply a compressive stress, you cause these moments to start rotating back to their initial state and draw a straight line through that relationship, and that's your call it D33 star. It's the relationship between the magnetic induction and stress. And those two couple. So this is that actuator I mentioned. So Toshiyuki Ueno has 3 of the little magnetostrictive rods and coils around them. And there it is moving. And then the other things that we've been doing here are more on the sensing side. There's a variety of energy testing types of devices. I've been working on these off and on with, this is iron gallium. The one you just saw was terphenol D. It's an iron terbium with a little dysprosium. This one's gallium and iron. And we make a bimorph where this one has an aluminum substrate and a galvanol on top. And we put it on a shaker and we predict the resonance. You get deflections. And as it bends, you get a current induced in the coil because you're rotating your magnetic moments because of applied stress vibration. This one's galvanol, right there. Yeah. The gallium. And then we also, they're very broadband. It's more the device that limits the bandwidth. Yep, they do DC. They actually do kilohertz and well into probably megahertz. I think you can still get something. Yep, yep. Yeah, Uwe Marschner, who's the German professor at Dresden that I've been working with, he's done sensors looking at the change in permeability of sputtered galvanol layers at high megahertz and uses that as a sensor. So, and actually right now my group's focusing a lot on aluminum iron alloys, alphanol, just as cost effective and arguably close to the same saturation magnetization, so should have the same sensing potential. So this is some work that there was actually an exchange student from Dresden that spent the better part of last year here did, where he was modeling the effect of the length of the coil and coil parameters, number of turns, and then got into using electromechanical system modeling to look at the effect of the load resistance to producing the optimized power. And device, this is what he built, lots of different coils. That's the bimorph there. He had a tip mass with a permanent magnet embedded in it to help with biasing, tip mass at the back, accelerometer measuring the input. And then this is the model of that. We couple force and velocity to moment and angular velocity to get the bending. And it's almost finite element-like. You see the little dot, 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 dot. So we use, try and get at least 5 to 10 elements per wavelength of interest in the region under the coil. And then in the region under the coil, we add the transformer that takes the voltage induced in the coil that's in proportion to the magnetic moment rotation. The part outside the coil is just a regular old bending beam that has a tip load and a tip moment of inertia out here at the very end. Yes, LT Spice. No, I'm not going to do it? Okay. In this case, what we did was we had a design in the lab that we modeled. And we get our transduction coefficients because the Yeah. What, a separate, yeah. Yeah. Yeah, I can't predict alloy compositions. No. What we did with a large study on terminal D was we built a very precisely tuned resonator that had one resonance, and as we varied the terphenol rods in the sample, you would get the loop shifting, the diameters would change. Yeah. Yeah. Well, you have to come up with your transduction coefficients that are physics-based, but.
But it would be nice to see what you get. Well, I mean,
I think he does a lot in the lab to come up with a design framework, and after he's got confidence, then he can extrapolate to new designs. Mm-hmm.
You know, I mean, so that's what I was wondering. You're probably the question. The complex are they different shapes and geometry and what thickness so they can work with, because especially if you want to fancy design, you have to have layers.
Yeah. They're a lot more skilled at this than I am, and they use these models to, they typically start with something that they characterize to get the transduction coefficients. And once they've got a transduction coefficient, then they design other systems based on that. Right. And they, like I said, they have one that comes to mind. Again, I'm most familiar with what they do using the galvanol or magnetostrictive materials, where they have a bone in plate sensor, where they looked at the bending loads on the healing rate, because as the bone builds around this plate, the stiffness of the plate changes, and so they were able to have an external sensor tracking the change in resonance of the saw device because of the change in permeability in the galvanol, because of the change in mechanical stiffness. I think it was, they had one that was for hips and one that was for broken bones. It's a plate, no, it's a plate inside the bone. It's inside the body, but they can still interrogate it. Yeah? Mm-hmm. They are, because they usually get a different texture, so the sort of cube lattice, the cube on edge, as opposed to a steady flat surface. So yes, they do get different properties. So they would characterize, they build a model, characterize it once they got, and that's what they did here. They iterated and got this model, characterized what the X would be, and then was able to run simulations at different G's and do some with different signs. That's the simulated and measured response, the open circuit, and then we put the load resistance on to tune the behavior and predicted and then measured. So we started with the first setup. Then we modeled and predicted what types of load resistors we would want to try. This is, again, the model measured very close. Output voltage, and then from the energy harvesting perspective, you'd want to know what the power output was. So there's going to be a trade-off in that as you add a little resistor, you're increasing the system resistance. And so even though the voltage goes up, your output power was actually peaked down, depending on your G level, at between 100 and 200 ohms. So I've got the next slide is the acknowledgements and thank yous, and then I'll go into the LT Spice demo, and my last demo up front here, which is going to show you that everything you've heard with me pulling the loudspeaker box off, you can see the electrical side. So, Professor Dr. Marshner hosted me for my sabbatical last year, so I had the opportunity to spend time there learning more. He actually sent one of his students, Maxim Germer, here. Maxim did that energy harvesting work. On the Maryland side, both Dr. Park and Dr. Na, senior associate and assistant research scientist in my group that helped with a lot of these materials. We wouldn't even have, right now, nobody makes alphanol except Dr. So that's exceptional. And then Professor Toshiyuki Ueno, he's one of the most accomplished magnetostrictive device designers and does all kinds of large and small. And then the National Academy of Engineering sponsored the German-American Friends of Engineering program, which is where I first met Dr. Marshner, and then leveraged both Humboldt Foundation funding to sponsor me going there and him coming here, and then Owen Armory on Magnetostrictive allowed him to come spend a semester here. So with that, let me fire up LT Spice for a second. And this is partly to show you, let's see. So there's my simple 1 degree of freedom system, and it won't be a big surprise that was it just running. And if I look at I'm not getting the graph. The demo isn't working. Let me go with it. I have another one here. I can just, that's why. It was closed. Okay, so this is a more complex model here, where I vary the mass and I vary the damping just with these commands. And I run it, takes a little bit longer, and it pops up a window that fast. That's what I was expecting to happen on that other one. And then I can, for instance, go down and I can put a current probe to measure force. And there's my multiple forces. I can switch to linear units and do a zoom in that region. That's where I got that part. So it's very fast once you get your model. And then blank this again, and maybe I'll blank it. Oh, I see. Well, in that case, I'll leave that out. What I will do is try and use LabVIEW to persuade you that what you're hearing with the effect of the speaker box is also very visible in the electrical domain. So let's see. I'm going to go 200 hertz. And my screen, I apologize if you have trouble seeing, you can certainly come up afterwards. I've got voltage to the loudspeaker on the top panel. I've got current in the bottom panel. And then as I pull this off, you can see the electrical signal. The current's staying the same because I've got a current source. But I mean, I'm sorry, the voltage is staying the same because I've got a voltage source, but the current is tracking what you're hearing as a difference at this low frequency. So that is why you might be interested in using these techniques to model something more complex. So with that, I can put Prince back on and take questions. So.
A little bit along the lines of John talked about. Now, all of these passive networks, the impedance is for positive real time. Now, the interesting thing is the inverse. How do you get a passive network from you want to design a certain impedance. And that's stuff in theorem that actually do that. Now, what I would say in the mechanical technique thing, to really be able to do stuff in sun. So, because that was an innovation. So I don't know how if you actually design and have an impedance one design. That's not really what I'm saying. Does it come in? I mean, that seems a reasonable inverse problem, right?
It does, it does. Yeah. I don't have experience with that, but I don't know if it's being done. Oh, no. Yes, you can. You, the analogy would be the energy harvester where I have a coil at one place, and so yes, you can model distributed systems with variable properties. Or damping, yeah. Actually, one of those plots showed the change in the tip motion. Yeah, and it tracks. The magnetostrictive energy harvesters, yes, we do them in my lab. Brooks is expert in applying galvanol. How small? They're about 0.5 millimeter thick.
Material.
Yeah, the thin. And actually, we also just published a paper on our nanowires. I don't make the nanowires. I get them from the University of Minnesota, and we've been characterizing them here and trying and showing we can make a pressure sensor out of them with the nanowires. Once you overcome shape anisotropy by controlling your aspect ratio, we can flip from vortex domains to domains that are in different orientations at the nanoscale. So if you want small, we've got some small.
But you're also looking into applications.
We're